I normally don't like to go through derivations. I don't think you gain a whole lot from them usually. But in this case, I do think that it is important that you understand where this is coming from, because it does actually give you an understanding of what's going on. And there's some important concepts that are going on here. So we're considering the special case of constant force. That's really key here, constant force. And in that circumstance, we can make some simplifications that work out and give us an accurate answer. So these are the four equations that we'll be working with. And in particular, this is the one, the V average equation equals V initial plus V final over 2. This is an important one. So in an earlier section, we did show that for constant force, the V average equation does give us an exact answer. So what we're going to do is we're going to come up with an equation for position as a function of velocity and net force. So let's go ahead and start out. So we've got our V average equals V initial plus V final over 2. Incidentally, we're just dealing with scalar quantities here. We're only considering motion along, in this case, the x-axis. These equations do work for the y-axis and z-axis, and we could write them as vector equations. We're just simplifying things for the purposes of derivation. All right, so from the momentum update, we know that P final is equal to P initial plus F net delta T. So we want things in terms of velocity, so go ahead and plug in P is approximately mv. We could do this with gamma and still get a similar result, but since in most cases we're going to apply this our low speed non-relativistic situations, we'll stick with the non-relativistic approximation. So we have mv final is equal to m v initial plus f net delta t. And let me go ahead and divide through by mass, because I ultimately want to be dealing with v final and v initial. So we're going to have a mass here. These guys cancel, and we're left with v final is equal to v initial plus f net over m delta t. If you've had physics before, you may remember this term right here is actually the acceleration. F net over m, that gives you the acceleration. All right, so what I'm going to do is I'm going to plug this equation in for v final right there to get an equation for v average. So v average is equal to v initial plus v initial plus f net over m delta t all over 2. So v initial plus v initial, that gives me 2 v initials, v initial plus f net over m delta t all over 2. And let me go ahead and distribute this factor of 1 over 2. And this will give me v initial plus 1/2 f net over m delta t. So that's my v average. Now if I want to go ahead and plug this into my position update equation, x final is equal to x initial plus v average delta t. So sticking this in for v average, we're going to get that x final is x initial plus v initial plus 1/2 f net delta t times delta t, and distribute the delta t through. We get x final is x initial plus v initial delta t plus 1/2 f net over m delta t squared. Forgot an m there. All right. So this hopefully looks familiar if you've seen a physics course before. This is one of the kinematic equations, one of the primary kinematic equations. And this is very helpful for calculating positions of objects subject to constant force. We can also turn this around and solve for time. There is an example in the text that goes through that. I do recommend taking a look at that so you understand how you can turn this equation around and solve for time. One other thing to really focus on in this section is the graphing motion. And right here I pulled one of the figures from the text, and so we have a y versus t graph for an object that's been thrown straight up and then coming back down. All right, so this is y versus t. This is not y versus x. So imagine you've got a ball starting down here. It goes straight up and then comes straight back down. So this point right here, this is the peak that represents the top of the motion. So the key to relating these graphs is the fact that we know that v is equal to dx dt. In other words, the velocity is equal to the slope of the position versus time graph. In this case, I guess we're dealing with y, so we'll call it dy dt. So if we look at this graph right here, we have a large positive slope. That means that our velocity is going to have a large positive value. As we go up, that slope gets smaller and smaller. We have a smaller positive slope here. We're going to have a smaller positive value. Right here, that's a horizontal line, the tangent to that point at the peak. That's going to have a value of 0, and that makes sense. We would expect the velocity to be 0 right at the peak of the motion. Now the object starts to fall. We have a small negative value there. We're going to have a small negative velocity, and then this is just, we keep on going where it gets more and more negative, just like this does as well. We can also tie in the force versus time graph or acceleration versus time graph. The two are very closely related since F is equal to ma in the low speed approximation. So the force here is simply going to be related to the slope of this graph. And the reason is that acceleration is defined as dv dt, and since force is mass times acceleration, we have that F is equal to m dv dt. So right here, this line is a straight line with a negative slope. That tells us that we have a constant negatively valued force. So if I were to go ahead and plot force versus time for this, here we have a large negative slope, large negative slope, large negative slope, and so forth, with the same value everywhere. And that's what we expect. When you're near the surface of the Earth, we expect the gravitational force to be in the negative y direction and to have a constant value. So it is important to take some time to learn these graphs and how they relate to one another. One last thing I want to focus on is the effects of the components of force on the motion. And what we like to do is break the forces into two components. One component of the force is parallel to the momentum. The other one is perpendicular. So what we have here is we've got the downward gravitational force, but we're considering it to have two components. This is the component of the gravitational force that's parallel to the direction of momentum. This is a component of force perpendicular. And so the effect of this parallel component is to change the magnitude of P. So this component right here is going to speed up or slow down the object. In this case, since the force is opposite the momentum, the object is losing momentum. The momentum is decreasing because of this part of the force. If we look over here, the parallel component of force is in the same direction as momentum. On this downward half of the curve, the momentum is increasing. Now the effect of the perpendicular components is to change direction. All right, so the perpendicular component is what causes this thing to form an arc. If we only had a parallel component, this thing wouldn't change direction at all. On the other hand, if this thing only had a perpendicular component, this thing would just go in a circle without speeding up or slowing down. So pay attention to this idea of perpendicular and parallel components. This will come up again in later chapters.